Hi, I'm Zor. Welcome to Unizor Education. Today we will talk about construction problems in geometry, primarily related to triangles. I have here, just for reminding myself of what kind of construction problems I would like to consider today, it will be a set of like 5 or 6 of them, 6 actually. I will basically try to explain how it's supposed to be done. In general, construction problems in geometry are very, very useful. It kind of confirms that you know the theory, but at the same time you know how to solve certain problems. In this case, how to construct certain geometrical object like a triangle. So that's why in the course of these lectures on geometry, I think I will pay a lot of attention to different construction problems. Alright, so a few construction problems which are very, very simple, and they are based on whatever the beginning of the theory of triangles actually is. The very fundamental theorems about equal triangles are at the foundation of these construction problems. So, problem number 1, construct a triangle by side, angle, and side. Angle is in between these two sides. Well, we all know that there is an axiom which says that if two different triangles have congruent pairs of sides and angle between them, then the triangles themselves are congruent. Well, what it means that we can uniquely construct a triangle by knowing only two sides and an angle between them, because any other triangle, whatever else we can construct using the same 3 elements, two sides and angle between them, will be congruent to any other triangle, which means again that construction problem is valid actually. Alright, so how to do it? So let's say you have 3 elements, 2 segments and an angle between them. Using these 3 elements we have to construct a triangle. Alright, well, what we can do actually is the following, and it's very, very simple. Since we have this angle, we can take in the compass the distance between these 2 points on the first segment and basically mark it here. And then take another side and mark another side here. So this segment is equal to this one. It's congruent, 2 different segments are congruent, and this is congruent to this one. So now we can just connect these 2 points together with using the ruler, let's say, and here we have a triangle. It has an angle given to us, and it has one side which has an equal length, since we are using the compass, which means it's congruent to a first segment, and another side which is congruent to another segment, which means we have actually constructed a triangle by these 3 elements, 2 segments which constitute their sides and the angle in between. Basically that's it, very simple problem. And again, considering all the triangles with congruent pairs of sides and angle between them, we have basically constructed any triangle which satisfies these 3 elements given to us. Alright, let's go to the next problem. Next problem is construct a triangle by 3 sides. Again, in this case it's not an axiom, it's a theorem about 3 sides. If one triangle has 3 sides congruent to 3 sides of another triangle, then the triangles are congruent. So, which means that we can actually uniquely construct a triangle by three sides. Well, how to do it? Very simple. If you have three segments, 1, 2, and 3, what we can do is take any segment, one of these three, that's too large, about this one, and put it on any line anywhere on the plane. Then, using the radius which is equal to the size of another segment, not equal to this one, we draw a circle using a center as endpoint of this segment which we started with. Then using another radius which is equal to a length of another segment and the center at a different point of the first original segment, we have another circle. Now, we have 2 points where these circles are crossing. Well, obviously, since circle is the locus of all the points distanced from the center on a radius, then this segment is obviously congruent to this one, and this segment is congruent to this one, because that's how we built it, right? And this segment initially was congruent to this one. That's how we started. So the whole triangle is congruent to the three sides of this triangle are congruent to three segments given to us initially. So, is that it? Well, no. There are some nuances here. And the nuances are related to the fact that if you have two circles from two different points of a segment, they might or they might not intersect. Consider this situation. If the segment we started with is too big and two other segments are relatively small, then these particular circles will have no intersections. Or they have something like one intersection, just where they touch each other. So we don't really have a triangle in these cases. What does it mean? It means that relative size of these three segments which are given to us is important. It was not the case with the previous construction problem where we had two segments and angle between them, because on the sides of the angle we can always put whatever the segments we want. In this case, since we are looking for intersection of these two circles, it might or might not be the case, which means that the whole problem of construction of a triangle based on three given segments, three given sides, is not always correct. It's not always valid. It doesn't always have a solution. It depends on the relative size of the segments. Now, to be absolutely precise, I can tell you that the biggest segment should be actually smaller than the sum of two other segments. Now, in this case, when these two circles are touching each other, then the length of the biggest segment is equal to sum of the lengths of two other segments. But if this length of the biggest segment is smaller, then there will be 2 points of crossing, and that's what we actually need. So the condition for validity of this construction problem is that the biggest segment should be smaller than the sum of two others. Then we can construct the triangle. Then we have actually two different solutions, but these two solutions are congruent to each other, because this triangle is obviously congruent to this one. They are symmetrical relative to this axis of symmetry. All right, so that's the second problem. Let's move on. What's my third problem? Okay, construct an angle equal to a given one, somewhere else on the plane. Well, it's very easy actually to approach this particular construction problem using whatever we have already done before. It's always like that in mathematics, in geometry in particular. You use what you have already accomplished to achieve whatever the new height you want in your logic. So in this particular case, how can I construct an angle equal to a given one at some other place on the plane? Well, very easily. Let's just take 2 points on both rays which constitute this particular angle, draw a line, now we have a triangle. And we know already how to build a triangle equal to another triangle if you have 3 sides, right? So basically using whatever the approach I was just explaining on construction of the triangle by its 3 sides, we construct a triangle with these 3 sides somewhere else, wherever we want to. Basically that's it. So let me just emphasize again, it's good, it's valid, it's the right approach in mathematics to say that this particular problem can be reduced to another problem which has been already solved by a very simple manipulation. Like in this case, we just draw a segment between 2 points on 2 rays of the angle and say, okay, the problem is solved because we know how to solve the problem of building a triangle by 3 sides. End of story. What's next? Angle, side, angle. All right. So if you have a triangle and you have an angle, a side, and another angle. Let's make it this way. Well, what it actually means, we have to transform all these 3 elements into a triangle so that this particular segment would be its base, this would be, let's say, a left angle, and this would be the right angle. Something like this. Well, okay, how to do it? It's quite easy, actually. What we can do is, we can have this original angle, one of these triangles, let's say this one, and have this segment constructed on one side of this triangle. So this is the segment which is congruent to this one. Now what we have to do? Now we have to build an angle which is equal to this one. Okay, how to build an angle equal to this one? Well, we know how. We just solved this problem, and basically we just, use it. If you want, we can do it again, but basically what I did, I took 2 points here, converted this angle into a triangle, and constructed triangle equal to this one by basically making a triangle equal to this triangle by 3 sides. So this is one side, this is another side, and another side. So I have all these circles, they're crossing somewhere, and so I get this point and this angle, and then just continue this angle until it crosses another ray of the first angle, and then I get a triangle. I mean, if you want, we can actually use exactly the same segment here to put this point, in which case this point will coincide with this one, and basically the same thing. Well, it doesn't really matter. It doesn't make the problem much easier. It just reduces number of points. So you have from here you have to draw a couple of circles here to get the point here. But in any case, we get exactly the same triangle, which will contain the base equal to congruent to our segment which we started from, and two angles on both sides. Okay, so that's the third problem. Third or the fourth? That's the fourth problem, actually. All right, next is how to bisect a segment. So if you have a segment, you have to draw a perpendicular bisect. Now, to do it, it's really quite easy, because again we can rely on certain theorems, and one of the theorems was that in the equilateral triangle, median and angle bisector and the altitude from the vertex down to the base coincide with each other. So what I will do is I will use certain radius. Let's say we can take the radius which is equal to this segment. Doesn't really matter. What does matter is that it should be big enough. And using this radius, I'll draw a circle, one and another, and they cross in 2 points, because I took the whole segment actually as a radius, so they obviously cross in 2 points. And what do we have right now? Let's consider this triangle and this triangle. They are both equilateral. Why? Because I took exactly the same radius from here and from here. So this line is equal to this and this and this. So these 4 segments are of the same length, congruent to each other. Okay. If that is true, then if we will draw the line between this point and this point, which we already have, and just connect these 2 points together, we will have this line, dotted line, which is what I would like actually to prove, that this line is a perpendicular bisector. But again, it's sufficient to prove that in both triangles, this line is the angle bisector and median and the altitude. Well, let's think about this. What's very easy to see is that this angle equal to this angle. Why? Because this triangle is equilateral with these 2 sides equal to each other. And in the equilateral triangle, angles at the base are the same. Okay, same thing I can state with these 2 angles. They're also the same. Now, the triangles themselves, this triangle and this triangle, are congruent to each other because 3 sides of one are congruent to 3 sides of another. So all these 4 angles are equal to each other. And therefore, this line is an angle bisector of this angle. And since it's an angle bisector, it's median, which means this point is the middle point of this thing, and altitude, which means it's perpendicular. And that's exactly what we need. We need a perpendicular bisector of a segment. So it crosses in the middle and perpendicular to this segment. End of story. We have constructed our perpendicular bisector. So again, we took this radius and made 2 circles from here and from here, and just connected with a line, the crossing points. Okay, that's done too. And bisect an angle. All right, what if you have an angle and you would like to bisect it? Well, there are actually many different ways, and what I can suggest is the following. Take any radius and draw a circle when it, crossing these two rays. So you have basically an equilateral triangle here with these two lines equal, these two angles equal, congruent to each other. And now what you can do is you can continue using exactly the same technique as before and construct the perpendicular bisector to this segment. How? Well, very simply. We take this radius and have another circle here and here. This point we already have, so now we will have just yet another point, and we have exactly the same picture. Now connect these, and it will be perpendicular bisector to this particular segment, which is at the same time median and angle bisector, which means these two angles will be congruent to each other, and that's how we bisect this particular angle. Well, that's basically it for these elementary construction problems. Now, what is interesting is that in the future, when we will discuss certain construction problems, well, I would say more complex ones, I will definitely use something like, all right, let's divide this segment in two halves, or let's bisect this particular angle, or let's draw a perpendicular line to this particular segment at this particular point, or whatever. And I will not really stop explaining how to do this. These are elementary bricks, if you wish, from which the whole building of geometry is built, construction geometry is built. So if you design a car, for instance, you don't explain how to make a tire. Basically you say, well, we'll take the tire, such and such tire, and put it here, right? Same thing with construction problems in geometry. You just use whatever the techniques have already been established, and these are just elementary techniques which I'm just offering, and there are many others. So whatever the new little technique will be, I will definitely explain it. Other than that, I'll just use it. So whenever I need it, I will just basically use whatever is necessary. Well, thanks very much. That's it for today. Hi, I'm Zor. Welcome to Unizor Education. Today's topic is construction problems in geometry. It's a continuation of some other construction problems, much more elementary, which we did before. We covered something simple like construct a triangle by 3 sides or something like this. Well, today it will be just a little bit more difficult construction problems. However, it's just a continuation, it's a progress, and I do encourage actually you to first take a look at the notes and all the construction problems which are presented, think about them, and then watch the video, and I will try to do exactly the same thing. Now, I deliberately did not spend any time constructing all these things beforehand to prepare for the lecture, so I will just think in real time how to do this. Construction problems which I will consider obviously have many different solutions, and I will offer mine. You can have your own, no problems with this. So without further ado, let me just start. Construct a sum of 2 angles. All right, let me maybe talk about this in more details, if you wish. What does it mean to construct a sum of 2 angles? Well, what does it mean to construct an angle which is congruent to another angle, to a given angle? Well, in some more details, it means the following. You have somewhere on the plane an angle, which means it's two rays which have the same vertex, which is the vertex of the angle. Now, obviously, when the problem says construct, let's say, an angle congruent to this one, it's not really specifically telling where to construct it. So I think to make the problem a little bit more precise, I think it should be given as well some other ray. Let's say this is A, P, Q, and this is B, let's say M. Now, having this angle on the plane and this ray, now more precisely the construction problem to construct the angle congruent to a given one should be like this. If you have an angle and a ray somewhere on the plane, construct another ray with the same origin as this one, let's call it Bn, such that the angle NBM congruent to PAQ. So the only thing which you really have to construct in this case is this other ray, because this one should be given. Otherwise, the problem is not really specified in all the details. So when I'm saying that I would like to construct... Now, by the way, before I continue with this particular construction problem about two angles, sum of two angles, obviously this particular problem has two solutions, because you can construct another ray, this one, and prime, let's say, and this angle will be congruent to this and congruent to this. You see, I put a little arrow to specify the positive direction of measuring the angle counterclockwise. So in any case, even in this particular case, when I specify exactly one of the two rays, there are two solutions, above and, well, on one side and on another side of the given ray, which gives basically the resulting angle congruent to the one which I need. All right, so basically it's important to specify all the details, but in theory you understand that if I just say, okay, construct an angle given to congruent to a given one, you understand it's somewhere on another plane, another place on the plane, and that somewhere should probably be given at least by the ray or something. All right, so let's not go into all these details and just go straight to the construction problem. So you have one angle and you have another angle, B, M, N. So but you have to construct an angle which is measured as a sum of these two angles. So angle PAQ plus angle MBN. Okay, question is how to do it. And again, let's assume, if we go to really, you know, the very scrupulous details, let's assume that there is some kind of a ray given to you, let's say CX, and you have to construct another ray, CY, in such a way that this particular angle is measured as a sum of these two angles. Actually, you know what? I made a very small mistake here. I should not really say PAQ, I should say QAP, since this is a positive direction of measuring the angles. So let's do it properly, counterclockwise. So it's angle QAP plus angle NBM. So, and this is an angle XCY. So, The purpose of this construction problem is to construct Cy in such a way that the measure of this angle is equal to sum of these measures. Well, how to do it? Well, it's obvious. You know how to build an angle which is congruent to the given one. That was one of the previous lecture, and so you build an angle first from this ray Cx. You build one angle which is called, let's say, XCZ. So angle XCZ is congruent to angle QAP. That's number one. Number two, using CZ as the new base ray, if you wish, construct an angle ZCY, which is congruent to the second one, NBM. Don't pay attention to this angle doesn't really look much smaller actually than this one. That's my drawing, that's okay. So basically you see that this angle would be congruent to this. Now this angle will be congruent to this. And that's why, by definition of the sum of two angles, the angle XCY will be congruent to sum of these two angles, or basically is the sum of these two angles. So that's how we build a sum of two angles. We are talking about measuring, obviously. Its measure of this new angle is equal to sum of these measures of the given angles. All right, so that's. I think I talked too much about this particular problem. It's a very simple one. By the way, if you forgot how to build an angle given to congruent to a given one, it's quite simple. You convert the angle into a triangle, and then build a triangle which is congruent to this one here, using three sides: 1, 2, and 3. 1, 2, and 3. All right, fine. Let's go on. We are wasting a lot of time on something which is extremely trivial. Next is a difference. Okay, if you have, again, one angle and another angle, and you would like to build a difference between these two angles, which means a new angle, the measure of which is equal to a difference between measures of these two angles. Well, obviously, if you have an initial base ray, you build first an angle which is congruent to this one, and then using this ray, you build an angle congruent to this one, but instead of going to the same direction, counterclockwise, you actually go counterclockwise. If you remember, to construct an angle given to congruent to a given one, you have two solutions. Remember, solution this and this. So basically, you can, in this case, construct the second angle using the second solution, if you wish. So whatever remains would be the difference. That's simple. And it's all based on the ability to build an angle congruent to a given one, which is done by constructing a triangle congruent to a given one. Given sum and difference between two angles, construct these angles. All right, this is just slightly more difficult, and it's a combination of algebra and geometry. Let's talk about measures. Let's say you have one angle which measures x, and another angle which measures y. So you are given sum of these things and the difference of these things. What you have to find out is you have to build an angles x and y given angles a and b. Well, let's approach this algebraically and consider this as a system of equations which you have to resolve for x and y. Well, how to do it? Well, since both equations can be added together, you would have 2x equals a plus b, from which x is equal to a plus b divided by 2. And if you subtract top minus bottom, you would have 2y equals a minus b, from which y is equal to a minus b divided by 2. So, given a and b, you have to construct x and y using these formulas. Now, how to do it? Well, very simple. If you have two angles measured a and b, how to construct a plus b divided by 2? This is angle measures a, and this is measures b. So first you build sum of these two angles, and that was just the previous problem, one of two previous problems. So this will be something like this. And then divided by 2, what does it mean to divide it by 2? Well, have an angle bisector. And again, you know how to do it from one of the previous lectures. So half of this is exactly what's necessary. So if this is a and b, this would be x. Now, if you have to build this one, again, a, and then b would be somewhere here. So you go backwards, right? This is a, and this is b. So whatever remains is a minus b, and again you construct the bisector of this angle, and whatever remains is your y solution. So that's how you build two different angles using their sum and their difference. So as you see, we have combined elements of algebra, which is how to solve a system, a very simple actually, a system of two equations with two variables, x and y, and the previous problems which involve how to add two different angles, or how to subtract one from another, or how to divide an angle by 2. Divide an angle into 4, 8, and 6 congruent parts. Alright, now you know how to divide it in 2, right? So how to divide into 4? Well, actually it's the combination of two things. First you divide it by 2, and then you divide it by 2 again. So if you have an angle, you divide it by 2 by drawing a bisector, consider the half of this, and then divide it by 2 again, another bisector. And that's how you actually do it even further. So this is 1/4, right, of the original angle. If you build another bisector, you will get 1/8, and another bisector, you will get 1/16 of the original angle, etc. So any power of 2, 4, 8, 16, 32, etc., can be achieved by sequentially dividing an angle by 2, and then divide the half by 2, and then the quarter by 2, and then the 1/8 by 2, etc., etc. And dividing by 2 is just drawing a bisector. So any power of 2 means just bisecting an angle more and more and more. By the way, some time ago I was talking about certain construction problems which can be solved using the ruler and the compass. And one of the examples of the problem which cannot be solved, and it's proven that it cannot be solved using the ruler and the compass, is trisection of the angle. So if you want to divide any angle in 3 equal parts, this is not possible to do in using the tools of elementary geometry. However, what is possible to do is to build an angle which is as close as we want to 1/3 of a given angle. And this is based on the following thing. In algebra, you actually supposed to learn something about infinite sequences. Now, there is a sequence so these are 2, 4, 8, 16, etc. powers of 2, but the signs are interchanging, the minus, plus, etc. Now, this sequence, if continued to infinity, gives a sum equal to 1/3, which means that if we will stop here, let's say, and just build this particular angle, then we will get, well, close to 1/3. If we will continue this process longer, we will get closer to 1/3. So the more time and efforts we spend, the closer to 1/3 we can get. Now, how to build this particular sequence of events? Well, that's simple actually. You start from the angle, you divide it by 2, and you get half of the angle, right? Then you subtract 1/4, which means you have to divide it by 2, and this is what remains. Then you have to add 1/8, which means you have to divide 1/4 by 2, and this would be 1/8. Then you have to subtract 1/16, so that would be this way, etc. So the more you continue adding and subtracting parts of the original angle, which we know how to do using the ruler and the compass, 2, 4, 8, etc. parts we can divide into. So using plus and minus, which basically, again, we have considered before in the beginning of this exercise, we can get as close as we want to 1/3, but we will never, in any finite time, we will never achieve absolute precision of 1/3. We will be only close to 1/3. Construct a triangle by its 2 sides and angle opposite to a bigger side. Is it always a unique triangle? So you have 2 sides, let's say this and this angle opposite to a bigger side. Well, how to construct this triangle? First of all, we start from the angle, since it's given, right? That's not exactly how it is. That would be a little bit more close to reality. Okay. Then we have a compass and we cut this particular point. So if this is A, B, C, and this is A prime, now this is B prime. So we just have an angle equal to, congruent to a given one. Then on one side of the angle, we basically measure the segment, one side of this particular triangle. And then using this as a radius with this center, we just draw a circle. Well, now here what's important, circle can actually cross in 2 points. Well, that's not exactly correct drawing, I'm sorry for this, but in theory these are equal radiuses and equal to BC, so we have C1, C prime, and C double prime here. So both triangles A prime, B prime, C prime, and A prime, B prime, C double prime are triangles which are which only one of them actually is congruent to this one, because this angle will be equal. But this is completely different triangle. However, you can build a triangle not always congruent to the given one, using 2 sides and an angle. All right. Now, it actually depends on the lengths of this particular side. You see, if this is the biggest side, then what's important is that it will actually cross this line in the second point, which is beyond the beginning of this angle. And this is not exactly the angle, the triangle which we want, because the angle is not given. It's a supplementary angle to the given one. So if this is the biggest side in the triangle, then there's only one solution. This is not a solution because the triangle would be different. This triangle would be not exactly the one which we need because the angle would not be the given one. So if the angle against the opposite to the biggest side of the triangle is given, then there is one solution and only one. Now, what if it's not? What if it's another angle? What if this is this angle and these two sides? Well, here again we will have different problems, different solutions actually. First, you start from the angle and you, using the compass, measure your side which is given to you. And then using this radius, you start circling. And now, as you see, we can have either two solutions, or one solution, or no solution, depending on how big actually this particular side is. So not all the combinations of segment, segment, and angle will give a solution or solutions. Sometimes you can have no solutions at all if this is too short for this particular angle, or it could be too long, and then you will have two different solutions, or it will be just equal, in which case you will have only one solution. So that's why there is no such thing as a theorem about congruent triangles where two sides and an angle not between them participate. If it's one of the opposite to one of these sides angle, then it all depends. Sometimes triangles can be congruent, sometimes not. Sometimes, actually, as I was saying, there are no solutions in this case. So that's why there is no such theorem as angle side side. In theory, there is no such thing. There is only like side angle side or angle side angle, but there is no angle side side. And this is why, basically. If it's the bigger side, then there is a solution. If it's not a bigger side, then there is none. Or zero. I mean 0 or 1 or two solutions, which means cannot be congruent. Okay. Construct an isosceles triangle by base and one of two other sides. Okay, so you have an isosceles triangle, you have a base and one of the sides. Now, how to construct it? Well, very simply. Let's divide it by 2. Can we have half as a leg, and then this as a hypotenuse, and this is the right triangles which we can build. And that's why we can build half of our triangle using right angle, half of the base, and hypotenuse. And now do exactly the same thing. That's how we build. That's simple. Construct an isosceles triangle by base and one of two congruent angles. Okay, same thing, very simple, reducing to right triangles. So if you have a base and one of two equal angles, how to do it? Again, using this right triangle approach. First we do half a base here, then using this ray we build an angle congruent to the given one, and then basically another half would be on this side. So we built an angle congruent to this one. That's how it's reduced. construct a isosceles by one of two congruent sides and an angle between congruent sides, the vertex. Okay, how to construct a triangle using one of the sides, congruent sides, and this angle. Again, very simply, by reducing the problem to right triangles. This is half the angle, so we basically have it, right? So what we do is, we have the line first, then we build an angle which is congruent to half of this, and then we cut these lengths on this side, and then draw a perpendicular and continue with the same lengths on the other side. Construct a isosceles by one of two congruent sides and base angle. It forms with the base. Okay. Again, very similar. So you have an isosceles triangle, and you have side and angle. Well, divided in two parts. How to build this right triangle by hypotenuse and an angle? Well, well, obviously, if we know that this is 90 degree minus this one, that would be easy. But if you don't know that the sum of two angles, two acute angles, is equal to 90 degree, you have this angle. Oh, very simple. Sure, you start with this angle, okay? You measure your hypotenuse and drop the perpendicular down, and then do it symmetrically. That's it. Very easy. So, as you see, I just hesitated for a second before I found the solution, which does not really depend on the fact that sum of two acute angles in the right triangle is equal to 90 degree. Because we did not really cover this in the lectures which precede these particular exercise, these particular problems. Okay, fine, so that's it. Don't forget to look at the website, unizor.com. It has many other interesting problems. And for parents and supervisors, that's a very convenient tool to supervise and watch the progress of your students. You can enroll your students into this or that particular part of this whole educational material. They can take exams, you can examine their scores and basically mark pass or fail. And if it's failed, then they have to really do it again and again until they basically pass all the exams. All right, so good luck and thank you very much. Hi, I'm Zor. Welcome to Unizor Education. Today is one of my favorite types of lectures. It's basically solving problems, a continuation of construction problems in geometry. Without any further ado, I'll just go through my list of problems, and obviously you have to try it yourself first. They're all in the notes for this lecture, and when you are done, just listen to the lecture and see if you are right, or I'm right, or wrong. Anyway, so let's go one by one. Construct a right triangle by its two legs. Right. Right triangles by two legs. Oh, these are legs, or catheti, as they're called in Latin sometimes. So construction is very simple. You start with the right angle somewhere. Now, how to start with the right angle? Well, obviously start with a line and choose some kind of a point outside and drop a perpendicular to it. Now, on one side of this angle, you basically, using the compass, you mark one particular side, and on another angle side, you mark another point, and just connect them. So that's easy, and obviously we are using the fact that this is the right triangle. That's why this angle is known. Basically, it's equivalent to constructing any triangle by two legs and angle between these legs. In this case, angle is 90 degrees, so it's known as perpendicular. Simple. Construct the right triangle by one of its legs, catetus, and a hypotenuse. Alright, so now we have other two elements. Usually it is sufficient to have two elements in the right triangle, three elements in the regular triangle. So we have one catetus, one leg, and hypotenuse. Okay. How to construct this particular triangle using these two elements? Well, very simple. Again, you start with the right angle. You use the compass to measure this particular side and mark the point here. Then using compass set to this particular side, to hypotenuse, you basically mark the circle with this as the center, and wherever it crosses this line, that's our triangle. Okay. Now all these problems are extremely simple, and what I'm basically doing is accumulating certain sets of simple problems, so in the future when something more complex comes along, I won't really go into the details how to construct, for instance, the right triangle by two catetes. I'll just say, okay, we know these two legs of this right triangle, that's why we can build it over there, construct it over there, without any details. So I'm continuing with these little things, small, simple. Construct the right triangle by a catetus and an acute angle it forms with a hypotenuse. Alright. So now we have this catetus and this angle. Okay, how can we do this? Well, as usually, if we know some kind of an angle, we should start with this angle. So let me start with this angle. I'll build an angle which is given. On this leg, I will mark a segment which is congruent to a given leg, and from this point I'll just construct a perpendicular from the point to this line, and wherever it crosses the other side of the angle, that's my third point of a triangle. Okay. Construct an isosceles triangle by altitude to a base and one of two congruent sides. Okay, so we have an isosceles triangle. We have altitude to the base and one of the sides. Now, when I'm saying that these are given elements, basically it means that somewhere on the plane there are two segments, 1 and 2. And what's given is, okay, this element is my altitude, this element is my side of the isosceles triangle. And using these two elements, I have to reconstruct or construct my triangle. So this picture is very helpful to analyze the problem. So what if, for instance, I have this particular triangle, so how does it look? Okay, this is my side and this is my altitude. But now, what do we see? We cannot construct immediately the whole triangle, but we can construct half of this triangle, this one. A, B, D. A, B, D. Since in the isosceles triangle, the altitude to the base and median and angle bisector and perpendicular segment bisector, they're all the same basically, then I can just construct half of this triangle and then construct another half by symmetry. So in this particular triangle, the half of the isosceles triangle, it's a right triangle because it's altitude. So I can construct it by the catetus, the leg, and the hypotenuse. So this is hypotenuse, this is the catetus. Now, I have already done, before this particular problem, a couple of other construction problems related to right triangles. I've done that already. So I'll just use basically what I have already done. I know that I can construct right triangle by hypotenuse and catetus. So I'm saying, okay, let's consider ABD. We have two elements of this right triangle known, which is hypotenuse and the catetus. All right, so I'll build it. I'm not going into the details about how to build it. I refer to the prior construction problems which have been already solved. So I can build this one. Now I continue this line and build the symmetrical point here. So these two segments are equal to each other, and that's my full triangle. Now why can I do it? Well, because the altitude is also a median, so it breaks the whole base into two halves. So I'm analyzing the problem first by drawing the picture of the ready-to-use triangle and see what elements actually constitute this particular triangle, and I know which elements I can construct. Actually, half of the triangle I can construct. Then I continue with another half. And again, notice that I have already used one of my construction problems, which I have done earlier about right triangles, in the subsequent construction problem when I had to construct an isosceles triangle. All right, what's next? Construct isosceles triangle by altitude to a base and an angle opposite to a base. Okay, at the vertex. So again, let's consider we have this already constructed. So what's known? Known this angle and altitude BD. Now again, we know that altitude to the base of an isosceles triangle is also a bisector of the angle and bisector of the base. So since it's bisector, consider again the right triangle and altitude. The right triangle ABD. What do we know about this right triangle? We know one catetus, the leg, because that's the altitude of the isosceles triangle. And we actually know this angle because it's half of the angle which is given. Now, angle ABC is given, so half of this angle I can consider as basically almost given. I can construct it. So how do I proceed now? I can construct ABD knowing the leg and the angle. So if I have an angle and altitude, So what I do, first I bisect the angle using this half, and in this segment I build the right triangle, and to complete the picture I just reflect this point to this side, so it's the same lengths, because it's a median as well, this one. Okay, let's go. Construct a isosceles triangle by a base and altitude towards one of two congruent sides. Aha. That's slightly different. So we have an isosceles triangle. So we have a base, AC. These two sides are equal, congruent to each other. So I have this, and I have altitude to one of congruent sides given. Now, well, obviously, as you understand, I can consider the triangle ADC. It's a right triangle, since this is an altitude, and I know hypotenuse and the catetus of this right triangle, so I can build it. So if my segments, this is AC and this is AD, this is altitude and this is the base. So using these elements, I construct right triangle. Okay, that's the beginning. Now what should we do? How can I get this third point of the triangle? Well, actually it's quite simple. What you can do is you can continue this line, and since this point B lies on the perpendicular bisector of AC, I can build perpendicular bisector AC, and that's where they cross. That's my third line. All right? And again, I'm not going into the details about how to construct a perpendicular bisector, or how to bisect an angle, or how to drop a perpendicular to a line, etc. All these elementary problems have been discussed in the prior lectures, and they should be at your disposal at any time. All right. Construct right triangle by hypotenuse and the acute angle it forms with one of the catenae. Okay. So you have a hypotenuse and this angle. Well, I think I did solve this problem before. Well, in any case, it's easy. You start with an angle which is given. You draw a hypotenuse. Oh, I think before I was solving when it was one of the catetus and an angle. Now it's a hypotenuse and an angle. All right, so you have an angle. Then you have this segment, so you mark it here. So this is your point here. And what you should do is drop a perpendicular to this line, and you got your triangle. Given an angle and a point inside it. Okay, angle and point inside it. Construct a straight line crossing this point and cutting congruent segments from the sides of a given angle. So I have to construct the line in such a way that these two segments are congruent to each other. Well, remember, one of the previous theorems or construction problems, whatever, we had was the following. If you have an angle bisector and draw a perpendicular anywhere to this angle bisector, then this perpendicular would cut congruent segments from both sides. Why? Well, it's obvious, since this is an angle bisector, these angles are congruent. These are right angles, since we draw a perpendicular to bisector. And this category is common for these two right triangles. That's why hypotenuses are equal to each other. So, how can I apply it to this particular problem? Well, first of all, it's good that I remember that particular theorem. Now I can use it. Now, how can I use it? Well, obviously I have to draw an angle bisector first, and from M I have to draw perpendicular to this particular bisector. Now, this perpendicular obviously is crossing the point M, which is required, and since it's perpendicular to the bisector, it cuts both sides of the angle in equal segments, equal lengths of the segments. So that's it. That's a very simple one. But you do have to remember, as you see, you do have to remember certain things. And that's typical in mathematics. You always have to do something new based on something which you have already learned and basically know. Okay, construct two segments but they're given sum and differences. It's similar to the angles, actually. We already covered this with angles. So if you have two segments, x and y. Now, you are not given these two segments. What you are given is sum of these two segments, called A, and difference of two segments, which is B. So the A is equal to x plus B, and B is equal to x minus y. All right? Well, actually, let's draw a little smaller. Now, what should we do now? Well, obviously we have to solve this particular equation for x and y, and that's very easy. You just sum them up. It will be a plus b, which is equal to 2x, and if you subtract one from another, it will be a minus b equals to 2y. And as a result, you have x equals a plus b by half, and y equals a minus b by half. All right? Let me make it prettier. It's a little longer. So the difference is b, and sum is a. Okay. So now, knowing a and b, we algebraically solved for x and y. So how can I construct these two segments, x and y, if I know a and b? Well, elementary. I just add a plus b and divide it by 2. How to add two segments you have to basically know. You just draw one of them equal to a, and then continue with another. And then how to divide it by 2? Well, you draw a perpendicular bisector. So half of this is a plus b divided by 2. And that's exactly the x which we need. Now, similarly, how to construct a minus b divided by 2? Well, you construct a again. Now you construct b to the opposite direction, towards another end of the first segment. And this one, whatever is left of it, a minus b, you draw a perpendicular bisector, and this part is your y. Okay, and the last but not least construction problem for this particular lecture is how to divide a segment into 4, 8, 16, etc. parts. Well, again, it's very similar to whatever we did with angles, and basically the solution is exactly the same. Since you know how to divide a segment by 2, you just draw a perpendicular bisector. That means that you can continue this process of dividing by 2. So if you divide this particular part, which is half, again into 2, you will get a quarter. Then you will get 1/8, 1/16, etc. Now, I actually addressed a very interesting problem when discussing the angles about how to trisect an angle. And I told that it is impossible to do using the standard tools of geometry, compass and the ruler. With segments, it's completely different. You can divide segment into any number of parts, 3, 5, 27, whatever you want. Well, there is a difference. I mean, there is a similarity between dividing segments and dividing angles, but this is the difference. So segments can be divided into basically into any number. All right, that's it for this lecture. Don't forget that there is a website, unizor.com, which contains all the different educational material, and it will definitely help parents and students, supervisors to control the educational process by enrolling the students into certain subjects, controlling their results of their taking the exams, score you can examine, and basically you can either check that this particular subject is passed or failed. And if it's failed, then the student must actually go again through theoretical material and exam questions until he gets, reasonable results. All right, good luck, and thanks you very much. Hi, I'm Zor. Welcome to Unizor Education. This lecture is a continuation of construction problems, everything about triangles, basically. And as before, I will be using certain things which I have already done before in the prior lectures. I'll use it just as known things, basically. Just for example, if, for instance, I'm saying, okay, let's construct the triangle equal to this one by 3 sides. I'm not going to explain how I do it. That's in the prior lectures. So let me go straight to additional construction works, construction problems, which I have. I hope you did spend some time with the notes for this lecture, where all these construction problems are written, and well, I'm sure you have been able to construct it yourself. So just in case you have some doubts, I'll do it myself. All right. Given a straight line and 2 points anywhere on the plane, construct a point on a given line equidistant to 2 given points. Okay. So you have 2 points and some kind of a line on the plane. What I have to find out is the point M on this line equidistant from AM should be equal to BM. I mean the lengths of these segments. Well, how to do it? I think it's appropriate to mention something which is called locus. Locus is a certain set of points, usually, which have certain property. Now, for example, what's the locus of points equidistant from two different points? If I have 2 points, and I need all the points which are equidistant from these two. Well, I claim this is the perpendicular bisector to segment which connects these 2 points. Why? Well, it's very easy to prove. Let's say point M is equidistant from A and B, which means this is equal to this. So the triangle is isosceles, and in the isosceles triangle, the altitude and the bisector of this angle and the median are all the same line, and that's why from M, perpendicular to AB will always fall in the middle of AB. If I will take any other point M prime and drop a perpendicular to AB, again, because these two sides are equal, the perpendicular will drop in the middle of AB. So no matter where my equidistant point is, it's on the same perpendicular which falls in the middle of AB. So the locus of all the points equidistant from two given points A and B is a perpendicular bisector to a segment which connects these 2 points. So what's the property this point must actually have? Well, it must be equidistant, because that's what basically the construction problem is all about, which means it should belong to the set of all the points equidistant from two given points A and B, which means it should belong to a perpendicular bisector. But at the same time, the construction problem is asking us to find a point on this given line which has this property. So basically we have an additional property. We have the property for the point M not only to belong to the perpendicular bisector of segment AB, but also on this line. Well, if the point belongs to two different lines, it's actually the intersection of these two lines, right? So if there is an intersection, that's a very important actually detail, then that's the point which we actually are looking for. So what we do is we connect A and B, segment AB, then we construct a perpendicular bisector to this segment, and if it crosses our given line, then the crossing point, which is only one, obviously, because two lines can cross in one point only. So this point is the one which we want, which we have to construct. However, let's just consider what if this perpendicular bisector and this line do not have any crossing points, which means they are parallel. So this actually also a case which we have to really think about. So if our 2 points are on the same perpendicular to this line, the perpendicular bisector will be parallel to this line and will never cross it, which means there is no point on this line which can be equidistant from these 2 points A and B. No matter what point we have, there is always a difference between the lengths of these two segments. And by the way, if you remember, one of the lecture was about perpendicular being the shortest distance from the point to a line, and the further from the perpendicular segment is from this given point M to this particular line. So this is perpendicular, this is the shortest, and the further from the perpendicular our segment is, the longer it is. So that's why if these lines are perpendicular, the line which connects AB and the given line, then there is no equidistant line on the M. There is no solution to this problem. Okay, construct a point equidistant to 3 vertices of a given triangle. All right. So if you have a triangle, I need a point equidistant to all these 3 points. Well, let's think about it. Again, let's approach this from the locus standpoint. The locus of the points equidistant from, let's say, A and B is this line. The locus of the point equidistant from B and C is this line. And the locus of the points equidistant from A and C is this line. Now, I cross them in one point, and that's obviously the case, but it needs certain comments. Why these 3 lines cross in one point? Because in theory, 3 different lines can cross this way, right? So this is not the case. This is the case. And let me explain why. Let me just assume an opposite, that the line which is a perpendicular bisector to AC crosses this way. So I have 3 points, M, N, and P. Now let me just try to prove that this is actually impossible. Look at this. The distance from the BM, distance from M to B, is equal to distance from A to M, because point M belongs to a perpendicular bisector. At the same time, since point M belongs to this perpendicular bisector, distance from A and C is the same. So AM is equal to AC. Now, from this, sorry, not MC, AC, MC. Or even better, CM, since I always put the vertex in the front. Now, what's interesting is that BM, this distance, is equal to AM, because point M is on this bisector. Excuse me. And AM is equal to CM, because M is on this bisector. So BM and CM are equal to each other because the equality is transitive, as we know. So BM is equal to CM, which means what? Which means that the point M should also belong to the perpendicular bisector of the segment BC, since it's equidistant, which means point M should belong to this perpendicular bisector of the segment BC. So that's why my initial claim that intersection is of this type is actually invalid, because the way how I draw it here, M doesn't belong to the intersection, to a perpendicular bisector. So basically this is not the case. What is the case is that all three lines cross in one point, and this is the point equidistant from all three vertices of the triangle. From A to point M, the distance is the same as from B to M, because M belongs to this perpendicular bisector, and this equal to this because it's this perpendicular bisector, etc. Which, by the way, means that if you would like to circumscribe a triangle into a circle, then the center of this circle is exactly here, because these are supposed to be three radii, which are supposed to be of the same length, since the circle is the locus of the points equidistant from one called a center. So basically, if you would like to circumscribe a triangle, then you have to find out the center of this circle by drawing at least two, you don't need really three, but at least two perpendicular bisectors of triangle's sides. Okay, let's move on. Given an angle in the straight line that crosses both its sides, construct a point equidistant to two sides of a given angle. Alright, now this is simple. Angle and line which crosses both sides, we have to find a point equidistant from both sides of the angle. Now, back on the memory line, what is the locus of the points equidistant from the sides of the angle? Obviously it's a bisector. From any point perpendicular to here or perpendicular to here are equal to each other, because the triangles are right triangles with common hypotenuse and congruent acute angles. So we have to find the point which is both equidistant, which means it's supposed to be on the bisector of this angle, and lying on this line. Well, obviously that's the crossing of these two points, so the construction is draw a bisector of the angle, and wherever it crosses our line, that's the point we have to, that's the point we're looking for. Okay, construct a point equidistant to three sides of a given triangle. Okay, we first made a construction of the point equidistant from three vertices. Now let's do distance from three sides. So we have to find the point where these perpendiculars have equal lengths. How to do it? Well, obviously, if you do this and these are equal, now these are perpendiculars, this is hypotenuse, and these are category, these are legs. So triangles, this one and this one, are congruent to each other, so these angles must be congruent too. So this is analysis of the problem. Now, therefore, basically, we have the solution. How to construct this point? Well, very simply. We just bisect this angle, then we bisect this angle, and then on the crossing we will have a point, and by the way, if we will draw the third bisector, angle bisector, it will also fall in the same point, and the proof is exactly similar to the proof of the point equidistant from the vertices. So to construct this point, which is equidistant from three sides, which means perpendiculars to the sides should be equal to each other, you just have to draw a couple of angle bisectors. And by the way, again, there is a circle involved here. If you will use this particular segment as a radius, then you can inscribe a circle into triangle. So the circle actually is tangent to all these three sides. We will talk about circle and its properties and what's the tangent is, etc. a little bit further, but just know that for now that this particular construction of the point which is equidistant from three sides, it is actually a construction of a center of inscribed circle. So there is a inscribed circle and circumscribed circle. Circumscribed around the vertices, inscribed between the sides. Okay, given a straight line PQ, 2 points outside but on the same side, construct a point on the line such that angles PXM, okay, PQ and points M and N on the same side. Construct a point X on the line such that angle PXM and QXN are congruent. Well, that's simple. You just take the point M, reflect it relative to this line, and if you will, draw a straight line from this point M prime to N. Now these are vertical angles, right? And these angles are congruent because M and M prime are symmetrical relative to this line, which means they are on the same perpendicular. This is equal and this is common, so the triangles are right triangles and they are congruent by two legs. And that's why the angles are also congruent. And that's why this angle is congruent to this, because these are vertical and these are congruent to themselves. All right, that's simple. Construct a right triangle by one of its category and sum of hypotenuse and the other categories. So we have the right triangle. Now we have this catetus, and we have a sum of this catetus plus hypotenuse. Well, which means if I will continue this line and make this equal to this, then the whole segment obtained. So this is A, B, C, and this is also C. So what's given is A and B plus C. These two segments. Now, how can we construct the original triangle? Well, considering we have A and B plus C, we can construct the big triangle, right? But now let's think about, since, well, let me put some letters, A, B, and C, so, and D. So if my triangle BAD, if you consider it, there are two sides which are equal to each other, which means this is an isosceles triangle, which means that perpendicular bisector to AB would be an altitude and bisector of this angle and the median of this triangle. So to obtain the point D, all I have to do is just take this segment and draw a perpendicular bisector. And now this is a triangle which I'm looking for, because this part is equal to this part, and this is given. So basically construct a big triangle, and from its hypotenuse draw a perpendicular bisector to get this point, and this is the triangle we are looking for. Okay, move on. Construct a triangle by side, an angle it makes with another side, and sum of two other sides. Okay, it's kind of similar. So if you have a triangle, and what's given is A, B, C, A, B, C, and this angle. So construct a triangle by a side, let's say it's B, this side, an angle it makes with another side, which is angle BAC, and a sum of two other sides, and A plus C. Okay, so these three elements are given for a triangle. What should we do? Well, basically it's very similar to the previous task, but the previous task was about right triangles, and this one is about regular, but we still have an angle which helps. So how to build this? Well, let's just think about, if you will, if you don't mind, I'll make it slightly different, smaller. Okay, this is B, and this is C, and this is A. Okay, so if you will continue this line by the distance equal to A, now what can you say about triangle ABC? You have a side, and you have another side, which is A plus C, and you have an angle between them. So you can build this triangle very easily. Now, this is A and this is A, which means BDC is an isosceles triangle, which means to find the point B, we have to do the perpendicular bisector to this side. And here is our point B, and here is our triangle, this one. All right? Seems to be simple, right? It's exactly the same as with right triangles, but instead of the right angle, we have a given angle. Okay, and this is my last one. Given an angle and 2 points, one on each side of an angle. Okay. Construct a point equidistant from both sides of an angle, and at the same time equidistant from two given points on an angle. Okay. So we need a point which is equidistant from these two and equidistant from these two lines. Well, again, that's a very simple locus type of construction. What is the locus of points equidistant from two given points? So that's the perpendicular bisector, right? It's this line. And what's the locus of points equidistant from two sides of an angle? That's the angle bisector. So the crossing of these two lines satisfies both requirements. It's equidistant from these 2 points because it's on the perpendicular bisector, and it's equidistant from 2 different sides of an angle because it's on the bisector. Well, that's it for this lecture. These are very simple construction problems, and they should be in your skill, basically, in your repertoire, if you wish, in your menu of available tools which you have to solve much more difficult problems. Now, what is important is to find out what kind of problem this is. Is it a locus problem, for instance, which means you have to just draw one locus, another locus, and maybe their intersection will be what you're looking for. Or maybe it's a construction problem which requires some kind of additional drawing which would help you to realize what exactly needs to be constructed. So maybe you, instead of constructing directly what you're looking for, you have to construct something else. Like if you remember in the previous task where we had one side and sum of 2 other sides and an angle, we basically constructed a bigger triangle, and then we decided what to do, how to find the point of the triangle which we really need to construct. So analysis is a very important thing. So first you have to start with analysis of this construction problem, and then if you really if you do it right, then you will realize how to do the construction itself. That's it for today, and don't forget, unizor.com is your site for all kinds of interesting educational material, and I would also like to encourage parents and supervisors to use this site to basically control the educational process, because the students can be enrolled, they should pass certain exams. You as a supervising person can control actually whether they pass or fail a particular lesson or lecture or whatever. So it's a very good tool to better educate your students. Thanks very much. That's it for today. Bye-bye.